Hi, Maria. I wanted to answer your question that you had emailed, and this is probably easier than trying to type out math answers through an email. So, your first question, as I look at simplifying this piece, where I'm told just to write it in A plus BI form. So, I do have some instructions like what I want it to look like when I'm done. Right now I can see there is an imaginary part right here, right? That's a negative radical. So I'm going to get my I out of that. And the work that you've written, I'm assuming is like you're writing what I had and asking the question. So I see that I got pulled out, which would leave me with 128. But with radicals, like fractions, you always want to reduce. So your first question was, why did I change that to 64 times 2? And the reason why is because that's just how you reduce radicals. I'm looking to see if there are any perfect squares hidden inside of 128. And since 128 times 2 is 64 times 2, and 64 is a perfect square root, that allows me to square root the 64 and pull an 8 out front. Now the 2 does not have any perfect squares in it, so I have to leave it in there, but then that gives me negative 8 plus 8i on the outside. Square root 2 is left in the radical over 4. Now the next part of it, you have written negative 2, which I assume is from dividing those two. Negative 2 plus, and then 8i radical 2 all over 4, which is good because you do have to, like, it makes a heart, you have to split it apart, right? This is going to be negative 8, putting another step in between. You'd end up with that, right? I'm undoing the common denominator here. If I re-added it and worked backwards, my common denominator is 4, and then negative 8 plus 8i would be what's on top. So I can see that right here, right, you reduced this one, became a negative 2. And then the question is, why can't you divide out a 2? And you have this highlighted. Now, because that is in a square root, it's kind of untouchable, right? That's not a 2. It's the square root of 2. So anything inside of a radical, outside of a perfect square, right? Up here, I can take perfect squares. Square root of 64 is 8. I can take those out. But anything inside of a radical cannot be touched by anything not inside of a radical. So I cannot reduce that 2. That 2 is like protected inside that square root. But I can reduce this, right? 8 divided by 4. So let me rewrite 8 plus, that would be 2i, and then the square root 2 is the square root 2. These things are all being multiplied. So I can pick whichever one I want to divide or whichever one's able to divide, but I wouldn't divide by more than one thing, right? If I had, I'm going to try to illustrate this with numbers. If I had 4 times, 6, let's make it 4 times 6 divided by 2. Well, 4 times 6 is 24, and 24 divided by 2 is 12, right? I know that's the answer. And I could have reduced way back here. I could have said 2 goes into 6 3 times, and 4 times 3 does give me 12 also. But I would never divide both of those by 2, right? I can't divide the 4 by 2 and the 6 by 2 with the multiplication sign in between. One of them gets divided by 2. That's just 24 total, 24 on top divided by 2, which I could do that. Now, if that was 4 plus 6 divided by 2, that's entirely different. That would have to be 4 over 2 plus 6 over 2, and I would divide both of those terms by 2. But this is one term. That's 4 times 6, period. So hopefully I answered your question in regards to that. I did attach your test, and I thought maybe we'd just take a little time to look at some of these problems, but this could potentially take forever, and I don't want to make the video really long, and I'm going to have to get going here pretty soon. So I'm going to pick a few of them. On the first page, we just had the identities, and those are just something that you would need to know and have memorized. At least these are really important as you go forward into the next class. They do come up again. Now, this first one, or I should, this main one, some students just choose to remember it, and then they use the Pythagorean identity to come up with the other two. Like the other two come from, remember you have this identity as well, sine squared plus cosine squared, whatever variable you want to use. I'm switching back and forth apparently between alphas and a's. So that's an identity I know to be true, and I could solve it for cosine. And then substitute this in for cosine, right? That'd be 1 minus sine of A minus sine of A. And then if I simplify, I'd get 1 minus 2 sine of A equals 1. Oh, my squareds got left off. There we go. And that is the one you have up here. To get the other one, all you have to do is go back and instead of solving for sine, for cosine, solve for sine. Move the cosine to the other side. And I know that sine is equal to 1 minus cosine. And when I mean squared. I know I didn't say the squared, but 1 minus cosine. And then if I simplify, I get cosine minus 1. Don't forget to distribute your negative, plus cosine equals 1. And I end up with 2, I'm running out of space, 2 cosine squareds minus 1 is equal to cosine of 2 alpha. Oops, I didn't need this. What am I doing? We're looking to see what how I can rearrange those. So that would be the third one that would have been written down here. So again, it's up to you. Some students decide to memorize all three. Some students decide just to memorize this basic one. And then if they need the others, they swap out sine or cosine for 1 minus cosine squared or 1 minus sine squared to find the other option. That would have been in chapter 3, section 1, or 3-2, either of those things if you want to go back and look at that. Number 3 is just a sign error. It looks like you had it right here and then just left it off in your answer. It just should have been negative. Now in this next section, there's lots of ways potentially you could go about doing this, but if you're taking calculus, it's really important to be able to use trig identities to like rewrite stuff to make it easier to solve. So that's what we're practicing here, or you're showing me if you know how to do here. This was in 3.1 and 3.2. Now, I'm looking at your work, and it is I think this is your sine over cosine that you've put here, and then I can see your tangent you've rewritten as a sine over cosine. I'm not sure where this cosine comes from, and then from there on your work gets off. So here is an option of how to solve this instead. Let's see. So I know sine over cosine. If I just do the opposite kind of what you're doing, if I write this as sine over cosine times tangent, just sort of separate it, I know that sine over cosine is tangent. And tangent times tangent is tangent squared. That's A. If I look at number 5, cotangent and tangent are reciprocals of each other. I know that the tangent of x equals 1 over the cotangent of x. And if I just rewrite this, cross multiply, this should have been like, any way you can rewrite an identity is also true. I know that two reciprocals times each other always equal 1. So this part right here is just a 1. Tangent times cotangent. Anything times its reciprocal is 1. And then tangent squared, if I make it its reciprocal, I'm going to get is cotangent squared. So moving tangent up into the numerator makes it cotangent, plus 1. And then I know I caught a crazy scary cat, right? It's written in out of order, but that is cosecant squared, which would be D. All right, one more The last one has to do with, I'm going to need to get a common denominator so I can add. Now, I can see here you've split this, like made this 1 over 1 and 1 over cosine. That actually doesn't work. You can only, if it makes a heart, you can split it apart, right? If this was 1 over cosine over 1, and what do I mean? Oh, I guess 1 doesn't really work, but so let's make it a 4. If it makes a heart, if it's top heavy, then you can split it apart. That would be 1/4 minus cosine x over 4. But that's not what we have. Excuse me. You can't do it backwards. I can't split the numerator. Like, think about that. If I were going to put this back together, I'd need a common denominator. I'd have to do cosine x over cosine x, and then subtract. I'd get cosine x minus 1 over cosine x, and this is definitely not what I started with. So you cannot split a numerator. You can only split a denominator. What you would want to do instead, anytime you see you have conjugates here, that's a kind of a hint that I'm going to multiply this one by 1 minus cosine. Whatever I do to the bottom, I have to do to the top. This one I'd multiply by 1 plus cosine. That would give me a common denominator. Notice, here are my two terms. Here's term 1, and here's term 2, right, separated by that plus sign. And my denominator is 1 plus and 1 minus cosine. So I have a common denominator. Now I can add. On top then, 1 times 1 plus cosine is just 1 plus cosine. Plus, over here I get 1 minus cosine. In my denominator, I have my common denominator. Now, I'm going to save myself a little bit of work. I could write them both again, right? That's my common denominator. But I know they're conjugates. And when I multiply that out, I'm going to get 1 minus cosine squared. That's how conjugates work when you do that. Now, I know then on top as I simplify, 1 plus 1 is 2. Cosine minus cosine is 0. So that's just 2 on top. And on bottom, I know that's sine squared, right? Sine squared, that's my Pythagorean identity, solved for sine, or for sine, right? If I solve for sine, I'm going to get 1 minus cosine. So this I could replace with sine. And then if I rewrite it in its reciprocal form, I get, which one is that? B. All right. You did great on number 7. Number 3, sum and difference identities. You did have it written correctly. All you needed to do is figure out 2 angles that are on the unit circle that add up to be 105. So, I don't know, 45 and 60 would work. It's not the only 2 that would work, but then you would have cosine of 45 plus cosine of 60. And you'd use the formula. Just remember cosine, the sign switches. So when you do cosine of the first angle, cosine of the second angle, it's going to be minus sine of the first, sine of the second. I'll let you finish that one. Number 9, it was just an issue of, again, you can hear my dogs in the background. It's an issue of just the whole fraction thing, right? You're good at this point. You plugged things in correctly. And then I think you got rid of this 2. You distributed that 2 to both, which does give me this 1/2. And then plus the square root of 3 over 4. It took me a minute to follow that. That's why my question mark got crossed off. But that is okay. What's not, I'm not sure. Let's see. It looks like you got a common denominator, so that this would be okay too. There's nothing wrong with that. But I'm not sure, like, these aren't like terms. You've got 2 plus the square root of 3. Those aren't like terms. I can't just write them next to each other like you did here. I would have to just leave that as 2 plus the square root of 3 all over the common denominator of 4. And then don't forget there was a square root symbol over the whole thing originally. So you were on the right track. You got really close. I think maybe radicals would be a really good thing for you to review. They do trip a lot of people up. In number 10, this is just to review that with inverse trig functions, if the inverse is on the page, right, you're not taking the inverse trig function like you do with equations, then there are only certain zones you're allowed to get your answers out of. Sine and tangent, you can only go up to pi over 2, and you can only go down to negative pi over 2. This was in 4.1. Right, so that's it, and you can't go through any other quadrant. So for this answer for tangent, I'm looking for where the tangent is radical 3, and that would be a pi over 3 angle, actually. You could look at your unit circle for that, or the chart, whichever you're using. So pi over 3, now I want tangent to be negative, so it's going to be down here, and my answer should have just been negative pi over 3. I'm going to rotate down pi over 3. This answer for an inverse trig function can never be bigger than pi over 2 or negative pi over 2. You're never going to have anything larger than that. And then the same is true here for the second problem. You're on the right track. You knew it was pi over 6. You have 11 pi over 6, which is in the right position, right? It is down here. Your answer would be this guy right here, which is 11 pi over 6 if you wrap all the way around. But for inverse trig functions, you're stuck in this zone. I cannot go past pi over 2 or negative pi over 2. That is it. So instead, I would have had negative pi over 6, not 11 pi over 6. That's why on that one, you only missed 1 point. Yes, so there you go. On number 11, let's see what happened here. So the tangent of theta, you're looking for an angle whose tangent is 4/5. Tangent is opposite over adjacent. I'm not sure why it flipped if you were just struggling, like couldn't remember which way. So if this is the theta you've picked, the opposite should be 4 and the adjacent should be 5, which means the hypotenuse won't be 5. The hypotenuse is going to be whatever 4 squared plus 5 squared square rooted is, right? You're going to have to do that Pythagorean theorem and you'll get something different there. So part of that was just creating your triangle incorrectly. You put the sides in the wrong place, which then, of course, no matter what you do, it's not going to give you the right answer later. The next one, the problem with this one really is I think you're using the wrong formula. The sine of 2x is, well, no, maybe this is what you had, 2 sine x cosine x. So that is correct, but I'm not sure what this is. I got a little lost. You do end up, it looks like, in the right spot. This is the right answer. So I don't know how you got there. Can't quite follow your work. And the only thing here, I'm just asking you to reduce. You've got 2 over 16. You can't touch the thing in the radical, right? The radical is protected. But 2/16 can reduce to 1/8. So it doesn't look like I've marked any points off for that. That is just your answer. Cosine of 2x. You use this formula, that looks right. The only thing is when you square a negative, it's going to end up being positive. So instead of 1 plus 30/16, it should have been 1 minus 30/16, which gives you a slightly different answer. But overall, you used the right formula and you did everything correct except for that sign error. Now, in this next question, it's asking you what quadrant you're in, and you said 3, but you got a positive for the sine and you got a positive for the cosine. So the only place that happens would be in quadrant 1. So based on the answers you got, you should have answered quadrant 1. So that's why I missed that one. And then down here for tangent, everything looks good. But again, this can be reduced. 3/15. 15 is stuck inside. There's no perfect squares that go into 15, but 3 over 15 could be reduced to 1/5. So because there were 2, like you could have reduced twice, I did take half a point just for, like, you got to start reducing. Let's see. On this next question, this was actually correct. You just reduced wrong. Like, this answer's fine if you wanted to rationalize then. So 2 over 5, radical 5. The radical's the only problem. I would have just multiplied by radical 5 over radical 5, which would give me negative 2 radical 5 in the numerator, and 5 times, radical 5 times 5 is another 5. You get negative 2 radical 5 over 25. That's how I rationalize that. This is not rationalizing. So I would practice that. You're going to want to be good at that, because that's, going to stick around at least for this next chapter. But this answer was correct, and if I didn't take any points, but it is a good idea to learn to make sure you can rationalize something like that correctly. In this next one, you did the problem correct, but you just reduced funny. So you had this, right? And then you knew you can flip that, multiply by the reciprocal, which is just fine. Now, if you had reduced right here, you would have gotten the answer, which is 11/2. But that's okay, you don't have to reduce there. The problem here was you multiplied across and got 66 over 12, which is correct. But then, I know this is just a silly error, but then you divided the numerator by 3, and you divided the denominator by 2, right? And you're supposed to divide by the same thing. If you had, and you can do either, actually. Dividing by 6 will be the quickest way. The 6 goes into both. Dividing by 6 would have given you 11, and dividing by 6 would have gotten you 2. So you could have gotten it that way as well. But the majority of the problem you did correctly, and just had a little issue of a little issue of reducing. And then you said quadrant 1, which isn't technically correct, but for your answers, right? This was your answer, that's positive, and this answer was positive. So that would put it in quadrant 1 for your work. Okay, on the equations, for the first one I'm looking at here, right, you've got 2x plus 1, and it looks like you moved this negative 1 over and then said negative 1 minus 1 is 0. And I'm sure that was just a mistake of sign, but negative 1 minus 1 isn't 0 when you move that over. It would have been negative 2. And then you end up with divide everything by 2, and you would have gotten, where does the cotangent of x equal negative 1, which is the same place that it's reciprocal, the tangent of x equals negative 1, and then you end up with totally different answers. So you did solve this part correctly, although it does say put all solutions, so you should have done 90 plus 360n and 270 plus 360n, or some version of that. And you didn't do that either, and I was just generous and didn't take too many points. So B was factorable. I see you did the quadratic formula, but I think it just got you into trouble because this you can use the quadratic formula, but I think you just had, again, sign errors here. You moved over this, right? So you have your negative sign minus 3 sine x, so that's fine, but the 1 should have been negative 2. You moved it over, made it equal to 0. I would have at that point, because this gets kind of messy, and I'm fine. I like how you changed it to a y. That's a good idea. I would have divided the whole thing by negative 1, just because all those negatives would make it difficult for me to see. And I'm allowed to do that as long as I do it to all the sides. And then now I could factor it. This would be 2y and y, 1 and 1. I just need to make the middle 3, so if I make them both positive, that would work. So it would factor as 2 sine plus 1 and sine plus 1 equals 0. And then you don't need the quadratic formula. The quadratic formula could have totally worked, but I think it went off again because your C, that should have been negative 1, which would have made that negative, which would have made a lot of different, I think then this would be negative, and 9 minus 8 would be 1, and then you wouldn't have had that square root of 17. So, watch signs. In number 15, let's see how much more we have. Okay, I can do it. In number 15, I've got an equation and it has sines and cosines. So I need to get rid of one of the others. Excuse me, one or the other. You did write the trig identity here, which is really good. That means I could potentially replace, I guess I'm going to replace the sine. I'll say that the sine squared equals 1 minus the cosine squared. I forgot my x. And then plug that in for sine. So I'm going to rewrite this cosine squared equals, but instead of sine, I'm going to put 1 minus cosine squared. And then now I only have cosine squareds. I'm going to move this one to the other side. That makes it plus another one. So I've got 2 cosine squareds. 1 plus 1 is 2. Divide everything by 2. So I get cosine squared equals 1. I square root, and remember when I square root, it's going to be plus or minus. So I'm looking for where the cosine of x equals 1. I know cosine of x equals 1 here at 0, and I know cosine of x equals negative 1 here at 90 degrees, or pi over 2. What did it ask for? Radians. So, and not a pi over 2, that's pi. So 0 and pi. So x is either 0 or pi, and I could write that as 0 plus pi n, because it did say all solutions. That would catch them all. I could put pi plus pi n, which would be kind of weird, but I could. I could just put pi n. That is all, every pi. This is an answer, and this is an answer, and this is like every time I rotate around to the next x-axis, cosine will equal positive or negative 1 there. So if it didn't say all solutions, you would have just said 0 and pi. Since yeah, that's one trip around the circle. It is true at 0 and at pi. But the answer we were looking for was this. This one, so anytime I have multiple trig functions, I'm going to move the tangent over, but I can factor out this tangent. I'm going to pull out the tangent. I'd be left with 2, cosine minus 1. Now I can solve. So either the tangent of x equals 0, or 2 cosine of x minus 1 equals 0, and I could solve for both of these. I want all the x's where the tangent is 0, which would be 0 and pi again. And if I'm going to write it as an equation, then it would be 0 plus pi n, because they're equal distance apart, just like the one I just did. And then the other one, I'm going to have a cosine of x equals positive 1/2, and then I consider where does the cosine equal positive 1/2? Well, it would be here at 60 degrees, or I guess we're doing radians, so pi over 3. I'm up at the pi over 3 angle. And then in this quadrant as well, cosine, all students take calculus. Cosine is also positive down in the bottom. So my pi over 3 angle here would be 5 pi over 3. So those are my 2 equations. And if I want all solutions, if it's only just the solutions from 0 to 2 pi, let me just double check. Oh, I'm so sorry. It does say in the interval from 0 to 2 pi. So this would be my answer, not this. I don't need the equation. And then these would be my answers. I don't need to worry about the 0 to pi and pi over 3 and, 5 pi over 3. Number 16, you did get this correct, but you only listed the positive answers, and you did have the negative sign. So it looked like you knew that you would want both. So when you're looking at where the cosine equals radical 3 over 2, well, cosine equals radical 3 over 2 here at pi over 6. And then down here at 11 pi over 6, both of those are positive, but negative answers work too. So I could also have 5 pi over 6 and, and it's in degrees, sorry. So 30 degrees, 150, 210, and 330. So all of those would have been solutions, and you only listed the ones that were positive, but otherwise you did the question correctly. All right, you did get the extra credit question. This one, you got 5 points for that, so well done. And the second one, it's okay. I think this video has been long enough. So hopefully that helps. And if you have any other questions, feel free to let me know.